first order kinetic coefficient of that bar. And for external gears, you want to memorize the sign is negative. Okay. So just trust me with this. Memorize that relationship is going to be extremely important. Something you'd want to write on a cheat sheet and refer to in an exam. Okay. Now let's look at internal gears. Okay. Very similar here. We have consider the two internal gears J and K that contact at point C, with rolling contact only, of course, because they're gears. No sliding is J1. Okay. And that's, of course, the instant center. That's where they have the same velocity. Okay. Suppose we draw vectors Rj and Rk from the center of the gears to a point on their pitch circles. The magnitude of these vectors are the radii of the gears rho j and rho k, and their directions are described by angles theta j and theta k. Okay, so theta j and theta k capture the rotation of the outer ring that rotates around that point. That's theta j and theta k. This is link k, and this theta k captures this rotation. But now I want you to visualize a bar that connects these points here, just like the other one, and its magnitude is rjk, which is rho j minus by rho k is that length. Okay, so if you take rho j minus rho k, it's the length of rj. Okay, that's its magnitude, and its angle is going to be a horizontal here, theta c. Okay, and it's always going to point to c where these things touch. That's why it's called theta c. Okay. Okay, so if you understand that, and you can imagine link J and K, and you've got a bar here that's basically C, and you can visualize this, it's very tricky. And you might want to try saying, like, oh, okay, what if I rotate this link this way, and I rotate this guy this way? Can you visualize what direction that's spinning in? It's very difficult. It depends on the speeds and everything. Okay, so we're going to do the math to solve this as well. And it's going to be very similar. Okay, so we're going to use the velocity difference equation to find what the velocity of C is as if it were a point on K, and we're going to equate that to the velocity of point C as if it were on J. Okay, so first, let's crawl from. Let's find the. Let's assume let's have the link here, link C or something. Okay, and we're going to find the velocity there is going to be 0 plus omega C cross RJK, which is rho C. The magnitude is going to be this, and it's going to be pointing in that direction. Just assume omegas are always positive, right, when you're thinking these out. Okay? Okay, and now we're going to go from that point to that point, which is C on K. And we know the velocity at that point, we just calculated as this. And now we're going to say omega K cross the vector that goes from there to there, which has a magnitude of rho K, is going to be this, rho K, or omega K, rho K, in that direction because you assume positive. Okay? If that confuses you, go back to the last example, and we did the same thing. We assumed everything's positive, but because C was on the other side, this went in the opposite direction. So in the internal case, we truly have this plus this, positive, because green and blue are both in the same positive direction, so we add them. And that is the velocity of C on K. Okay? Now let's find the velocity of C on J. So if this was rotating, we have the velocity, this is 0, and then we take omega J cross a vector that points from there to C, which is just rho J, and it's just that. And it's also positive. Okay? So we set these equal because we know that that's the instant center of J and K, and they have the same velocity there, and it's rolling contact only. Okay? And so we set them equal. And now recall that rho C is rho J minus rho K. Now I want you to put me on pause and do your math and find the relationship of rho K to rho J again. Okay? Okay, if you've done that, I'm going to give you the answer. It's this. Okay? And again, we're going to do this first order kinematic coefficient transition here and convince you that these equal. Okay, we're going to cancel that out. And so that means this equals that, and so that is the answer. And again, notice it's basically the same equation as external. J was here on the top and here on the bottom. K is here on the top and on the bottom, and here's the C thing with minus. The only difference in this equation, the last equation, is this is positive. There's no negative. So basically, if I just take this equation, put a negative there, it's for external gears. If I make this positive, it's for internal gears. So it makes it easy to memorize for both. And all you need to remember is internal gears, it's positive. Okay? Okay, so we've done it for the two different kinds of gears. Now let's look at the third type, which is essentially rack and pinion. Okay? This one is a little tricky because it's a little different here. So consider gear J and rack K that contact at point C with rolling contact only, no sliding. Again, of course, imagine the teeth on the rack and pinion, they can't shear, they're only sliding, so that's where they'll have the same velocity and everything, right? Okay, because it's rolling only contact, okay, and the velocity in both tangent and normal components have to be the same, okay? Suppose we draw a vector rj from the center of the gear to a point on its pitch circle here, and so obviously theta j is going, so these are 2 points on j, this gear, and theta j is going to capture the rotation of the gear. Okay? The magnitude of this vector is the radius of the gear rho j, and its direction is described by theta j. Okay, this angle represents how much the gear has rotated. Now suppose we draw another vector, and this is the confusing one, rjk, that points from gear j's center to C, where rack k touches the gear. Okay. Its magnitude is also rho j, but its direction is described by theta c. So now we're going to take vector that points from here to there. And that's not necessarily point. So this is a point on j, but that's not a point on j. It doesn't move with j. If it did, it would be the same thing as the derivative of theta j. It would have the same rotational information, right? Instead, this is always pointing to where the k and j touch. And it's always going to be 90 degrees to it. Okay, it's always going to be perpendicular to it. But it itself has its own rotation. And I kind of wish they hadn't drawn it this way. I'd like it to be horizontal all the way around there as theta c. But they did the vertical to there as theta c. And it really doesn't matter because we're going to look at the speed. We're going to look at omega c or theta c prime, which are both basically the rate that theta c changes as a function of time or the input variable. And so it really doesn't matter whether you do horizontal or vertical there. But just know that theta c captures the position of that vector, which always points to the touch, okay? Before in the analog, that pointed to the center of either the ring or the gear circle. This is pointing where they touch, okay? Finally, we draw a vector rk from C, where they touch, to the end of the rack as shown, right here, rk, okay? All right. The time derivative of the magnitude of this vector is the translational speed of the rack on top of the gear. So if you imagine the gear just pinned here and this rack is flying on there, the rate that changes is how fast the rack is moving. Okay? The vector's direction is described by theta k. So you could imagine the rack could actually rotate around this gear, and the theta k here is going to capture that angular rotation or position of rack k. Okay? So it's a little tough to wrap your mind around here. The rate this angle changes is the same as the rate that theta c changes. So notice omega k and omega c, or theta k prime and theta c prime, are the same because this is always forced to be 90 degrees or perpendicular pi over 2. And so as theta k changes, theta c is going to change the exact same amount. So theta k and theta c, as they're defined here, are the same, but certainly omega k and omega c are the same. The rate that they change is the same. Okay, and notice that rj and rjk both are just rho j. Okay, so now you kind of understand this. Let's do the derivation of this. Okay, this is, I think, much more difficult to visualize than anything because, not only can this gear rotate, but the rack and pinion can rotate and it can translate along touching there. So it's very difficult. But we could look at the system as if it consisted of two external gears. So remember the external gear equation, except where one of the gears, k, has an infinitely large radius. Okay, so remember when we do external gears, this was the equation where, see, j's on top, j's on bottom, k's on top, k's on bottom. This is the c thing. and this was negative because it's external gears. Okay, so if you do that, but imagine, and by the way, let's move this around. So let's times rho j by this and times this by rho k. So you get this. You imagine this equation is the same as that. Basically, we've just moved it around. Now let's make rho k, right, the infinite. Because remember, if this was for external gears, where the pinion one was j and the big one k was a giant circle, but now its radius goes to infinity. So if this radius goes to infinity, now this external gear scenario is matching the rack and pinion. And remember, for the rack and pinion scenario, this theta k prime and theta c prime are equal. Okay, they have the exact same angular velocity. Okay. The rate that they change with respect to the input is the same. So those will cancel, and you might as well just write this as theta k prime. Okay, so remember, in engineering here, infinity times 0 is always just any real number. It depends on how infinity is and how 0 it is, right? You think of 0 as c some number divided by infinity is 0, different flavors of 0, depending on how big c is. And there's different sizes of infinity, right? But if you times these two together, you can get basically any real number. Okay, so to write this equation a little differently for the rack and pinion scenario, you get theta j prime minus theta k prime, rho j equals just any real number, plus or minus rk prime. Okay? Okay, and so... Right. So that's that. What we did is we just took the external gear equation, made the radius equal to infinity of one of the gears, and massaged the equation around and got this equation, which is a very important equation. By the way, the sign of this you interpret by inspection. Okay. So let's. If I know that wasn't the most satisfying derivation, let's kind of try this out and kind of derive it. Pretend we already have the equation. Let's derive and see if it makes sense. Okay, so let's just simplify this, use this equation and simplify it so it's a little easier to visualize and prove to ourselves that this is a correct equation. Suppose we don't allow rack k to rotate. So theta k prime equals 0. Okay, so this is just stuck there. This is 0. We're going to make this 0 here. And now what we're going to get is rk prime, which is the speed this moves, is apparently rho j prime times... theta j prime times rho j. Okay? Well, if we allow rho j prime to rotate in a positive direction according to the right-hand rule, and k, is just fixed, it's not moving, then what you're going to get is you're going to get something like this. You see how it's kind of moving over, and the speed that it will move over is, of course, omega j prime times rho j. So remember, theta j prime times rho j, where you can think of this as a speed. Remember, omega j cross, if you've got a cylinder rolling on a flat, the angular velocity of that cylinder times its radius is, of course, the speed that it's going. Okay? And that's essentially what's going on here. If you allow this to be positive, you see it's going positive direction there, which is why this is a plus sign. Okay? So now let's look at a different scenario. Let's say, now suppose we don't allow gear J to rotate. So this whole thing's fixed. And so the angular velocity of this basically is 0, or the first order kinematic coefficient is 0. And now we're going to allow K to rotate in a positive direction. Okay? So we're going to keep theta K prime positive. Now watch this. With respect to the gear, the rack appears to move as shown above. Okay, so watch this. There it goes. When we're rotating K, it'll be going up like that. Now, the end result is this circle is near the end of K here. So another way to look at it is imagine K is fixed and this is actually rotating like that. That's the same relative motion. Okay, so another way to think of it is if we held fixed this, we allowed this to be positive, this is essentially, the J would essentially be relative to K as if it was moving in this direction with a negative sign. So it would be like theta K prime rho J, but in the negative direction. Okay? So do you see how, why this is positive, why that's negative, why those two things are in here, why they're rotating by this, and why this whole relationship adds up to be this, the speed that moves with respect to K. Okay, so by that little thought experiment, I show here, this is essentially rho J prime in that direction, or theta J prime rho J, minus theta K prime rho J in that direction. That's why you add, subtract, and you get this. Okay, so from that, hopefully you can see that this is a true equation, and if we just divide this by that, we get this, and this is what you'd memorize for a rack and pinion. Okay, so a little tricky derivation. Really stare at it a lot. Think about it. Make it make sense in your head, that external gear with the radius going to infinity derivation, and then this little thought experiment. Convince yourself that this is indeed a true equation. And this is what you'd want to write on a cheat sheet. That's the rack and pinion equation. Okay? Okay, so, all right, so let's do some thought experiments here. Let's say we're just going to have two gears that are pinned to the back plane. So that means basically the arm, the thing that connects these, you could think of, these guys are fixed to a link or a bar between point O and B, right? And if that's the thing held fixed, then that's basically just two gears stuck on a back plane. For that scenario, the theta C prime goes to 0, and sure enough, if you rearrange this equation, which, well, first of all, let me start. When you look at this, you can see this is obviously the external gear thing. So you'd write the equation. You ask yourself what's fixed. They say centers O and B are fixed. You kill that, and you schmooze it to this, and you can see, indeed, this is exactly what we knew. Okay, we know that the ratio of rho K to rho J is the ratio of these angular velocities, so to say. Okay, we began with that in the lecture, proving that for gears stuck on a fixed background. This is essentially the ratio of their speed, or omega J to omega K. Are these radii. We proved that at the very beginning of this topic. Except now we're careful. We have a negative sign. Before we weren't careful about the negative sign, and this negative sign basically says if J rotates in a positive direction, K is going to rotate in a negative direction. If K rotates in a positive direction, O rotates in a negative direction. We weren't careful about signs at the very beginning of this topic. We just found that the radii ratio equals the angular velocity ratio. Here we derived it using, from the most complex equation, simplified it, and we do account for the sign in there. Okay, now internal contact with fixed centers, say the arm that connects those is 0. So you do the internal gear equation where there's a positive sign here. It's the same equation as the last, but it's a positive sign. This guy goes to 0. You change the relationship, and there we go. That's that scenario simplified. Okay, now say it's a little more interesting. Here they actually finally draw the bar, and now we fix this. So now this gear is actually held fixed. So to find the kinematic relationship of that, again, you notice, it's external gear equation with the negative sign, except now we're going to make theta J 0 because it's fixed. It doesn't have any rotational velocity. So its first order kinematic coefficient is 0. And this one can actually move. The bar can actually rotate, and K can actually rotate. So you massage these, and the ratio between C to K, or the angular velocity of C and K, is this. Okay, same thing with the internal gear one, same equation with positive. You make this one 0. This one, the arm can now rotate, and K can rotate, and you get this. Okay, so you can see how these equations kind of work. And we can work our way up to the most complicated of these things, which is the Epicyclic gear trainer planetary gear set. Okay, I don't know if you've seen these, but these are all over transmissions within cylindrical packaging like drills or any electronic drill sort of scenario has these motor-driven mechanisms have these planetary gear sets inside to achieve different transmissions. Okay, and the reason they're called planetary gear sets is because there's a sun in the center, and there's these planets that usually revolve around it. Now, in this case, this outer arm that's like the body that pins all the sun and the planets together is what's being held fixed. So the planets don't appear to be revolving around it. But if you allowed the arm to rotate, say, and you held the outer ring fixed, which is very common, then you'd see not only would the sun be rotating, but the planets would be rotating, revolving around the sun. Okay, so this is called the ring, that's called the sun, that's called the planet, and this is called the arm. Okay. Okay, so these can be super difficult to visualize. If I didn't teach you what I taught you, visualizing, if the arm rotates clockwise at some speed, and the ring rotates counterclockwise at some speed, how is the planets rotating? How is the sun? I mean, it's very difficult. So I'm going to give you the math to do this. And you actually already have it here. So we just need to manipulate what I already showed you here. So say you have this scenario. Here's the ring. They have it labeled 1 for ground. They're saying this is actually fixed. But it doesn't matter. The math will work whether it's moving or not. Here's the sun. It's 2, link 2. Here's the arm, it's link 4, and we're just going to show one planet, link 3, okay? And you can imagine if there were 2 other planets or 4 other planets, it really doesn't matter the number of planets, you'd want them all to be linked by the same arm like this, okay? Here we just got rid of the other planets and had the arm go from there to, like, say, there. And we're just looking at one sun, okay, to make it easier to visualize. Okay. So what I want you to do is, in analyzing this, let's just look at what's true. Just ignore the ring and just see the sun to planet situation there. It's essentially the external rolling contact equation. And so notice that how we label this. 3's on the top here and on the bottom here. 2's on the top here, on the bottom here. And this is 4, the arm, okay, where, sun is here and 3 is the planet. So, and because this is external contact, these are 2 circles touching externally, we make this negative. Okay, so that's a true equation, and we've labeled it correctly according to the link numbers and everything. But now let's say, okay, let's forget about the sun, just pretend the sun isn't there, and say we have the ring with this arm going to the planet. Okay, now this is if you just ignore the sun, pretend I just didn't draw the sun and I just left 4, 3, and 1, then you could draw the internal rolling contact kinematic equation and make sure you label this correctly, where 1 is the ring on top and the bottom, okay, here 1, 1, and then 3 is the planet, okay, it's top and bottom, and then 4 is always the arm, and because it's internal, there's a positive sign there, there's no negative sign. Okay, so that's true. So now using these equations, we can massage them to get what we actually want. It's important to recognize that in these epicyclic cylindrically packed transmissions for drill presses and these different mechanisms, the only thing that's useful really is the ring, the sun, and the arm. I mean, the planets are necessary to get the transmission, of course, but the planets don't they don't rotate around the center of the outer cylinder. The others do. The ring rotates, its central axis is point B, the sun's central axis is point B, and the arm central axis is point B. And that's usually what you care about. The drill is going to be attached to the central axis of this. And so you really, those are the ones you care about. But unfortunately, in both of these equations, we have first order kinematic coefficient of theta 3 with respect to some input, whatever that input is. Okay? So I guess the question is, can you take these 2 equations, put me on pause, and massage them so you can find an interesting ratio only using theta 1 prime, theta 4 prime, and theta 2 prime, and get rid of theta 3 and find something interesting. So go ahead and put me on pause and try and find that ratio. So essentially eliminate theta 3 prime. Okay, so if you did that, I'll tell you how I would do it. I would solve for theta 3 prime with respect to this, and then I'd plug it in, and I'd massage things around, and you would get this equation. Okay, this is the equation you would use for an epicyclic or planetary gear set that tells you everything. Okay, and notice theta 3 prime's not in this. It just has the ring, the arm, and the sun gears, and we only care about the ratio. The only radii we need is the ring and the sun. Okay, we don't, of course the arm doesn't have a radius, okay? And so thank heavens that doesn't show up in there, okay? All right, so, okay, so now what we can do is if you want to, since it's very difficult to visualize, you could say, okay,